Welcome, and thank you all for joining us today for this webinar on understanding and resolving Java warm-up problems. Today, basically what we're going to be going over is Hotspot's lifecycle. While Azul does make another VM besides Hotspot, we make an OpenJDK VM Zulu and another VM Zing. I'm just going to stick to talking about Hotspot and OpenJDK today. But really, regardless of the VM you're using, they all work roughly the same. In most VMs, your code starts off running in the interpreter, and while it's running in the interpreter, the VM attempts to identify which code is hot, usually just using some simple counters. And then as your program continues to run, we'll also profile your code, so we'll go beyond just identifying the hot code, and we'll identify what your code is doing. Is a branch always true? Is a branch always false? What types flow through a call site? All sorts of things. And those are fed into the just-in-time compiler. In Java 8, there are actually two tiers to the two just-in-time compilers. One called C1, which is a baseline just-in-time compiler that also does profiling, and then another one called C2 that is our optimized tier, and it does what are called profile-guided speculative optimizations. That's a bit different from, say, C or C++, where we don't usually use profiles to guide optimization. But it turns out that's really important to optimizing Java. And C2 goes a step further than even a C++ compiler could do with a profile, and it does speculative optimizations, as in they can be wrong. And the downside of them being wrong is as your program runs, not only can it become more optimized, it can also become de-optimized. And we're going to see all of these things happen. To be a bit more specific, we're going to look at what triggers the JIT, what triggers de-optimization, and we're also going to look at a couple different types of de-optimization in Hotspot, as well as our VM Zing. There are 2 or 3 different types of de-optimization that can occur with different impacts on latency. We're going to look at the impact of all these things on warm-up, and we're also going to talk about why just sort of fundamentally ahead-of-time compilation is hard to do for Java. There are just certain things about the language that don't lend themselves to ahead-of-time compilation. So first, let's talk about what triggers the JIT. And we're going to do that by running a very simple program. This program, we're measuring the performance of a summation of 5,000 numbers. That's the part highlighted in blue in the middle of the slide. And just to make sure the just-in-time compiler doesn't get too clever and do an optimization called dead code elimination, I'm going to assign this to a static variable. And then I'm going to measure the performance of that summation by using system nanotime, and I'm doing that repeatedly in an outer loop that runs for 100 iterations, so we can see how the performance changes as the program continues to run. And if you were to run that program, you would get a table of results that looks like this. The program starts off running relatively slow, 75,000 nanoseconds to sum up 5,000 ints, at least on my laptop. But as it continues to run, around the 13th or 14th iteration, it suddenly gets faster. Goes to around 30,000 nanoseconds, and then to as much as like 13 or 14,000 nanoseconds. So a program suddenly got 5 times faster. And this is when the baseline JIT, C1, kicked in, because of a mode called tiered compilation that's on by default in Java 8. And then if we continue to run even more, we'll reach the optimized JIT. As you can see, somewhere around the 58th to 60th iteration, the performance improves to about 2,000 nanoseconds, or even a little less, for summing our 5,000 ints. So now we've gotten better by another factor of 7, and overall our program has gotten faster by a factor of about 50. And this is just what Hotspot does. As the program runs, it decides that certain methods are hot, and it just-in-time compiles them, first with a fast compiler that produces relatively slow code, but still much faster than the interpreter, And then as the program continues to run, it'll compile it with an even more intelligent compiler. It will take a little longer to compile, but the code that comes out will be even faster still. And just to see a visual for this, here's a plot of the same data. And we can see we start off in the interpreter at around 75,000 nanoseconds. This chart's on log scale. And then around that 13th iteration, we drop to close to 10,000, so about an order of magnitude improvement. And then one more roughly order of magnitude improvement to get to about 2,000, and somewhere around the 60th iteration. And individual methods really are going through this stair-step process all the time. And if you wanted to confirm that this was really happening, you could run your program with the incantation -xx : plus print compilation, which will show you the compiles that are actually being done by Hotspot. The format here is the leftmost column is the time in milliseconds when the compile was started. The second column is the compilation ID. They're assigned sequentially as the compiles are in-queued to a background thread. They won't necessarily complete in order. The third column is the tier of compilation. And the fourth part, the far right, is the name of the method and its size in bytecodes. And at the bottom, we can see the actual main for our program. And we're actually seeing something a little interesting here. We're seeing main show up several times, one at a couple different tiers, but we're also seeing this funny little % sign out to the side. That indicates that we're doing just a loop compilation rather than an entire compilation of main. And the @15 off to the right is the bytecode index, you can think line number of the loop. If you don't want to learn how to use that output, you can use a GUI tool called JITwatch created by a gentleman named Chris Newland in the UK. It will provide a GUI of the compilations that have occurred. It provides lots of other nice things too, like a triple view of Java code next to Java bytecode next to machine code. It's a nice tool to play with. I think it has limitations when we're looking at really large programs, but to just get a better understanding of what's going on, it's an excellent tool. JITwatch is reading a file that's generated by log compilation, which is -xx : unlock diagnostic VM options, and then log compilation. That produced as an XML file, which contains a lot more information than you can get from, say, just turning on print compilation at the command line. It will tell you when your compile was in-queued. It will show you all the different phases of the JIT. It will show you the installation, including things like the address at which it was installed. And we're going to refer to this file a lot more as we go along, because there are certain things that you just can't see in a product build of Hotspot without going into this XML file. Well, starting with Java 8, tiered compilation has been enabled by default in Hotspot. This is something we've had with Zing for a long time. But basically the idea is to marry the old client VM with the old server VM. The client VM used a JIT called C1, which was designed to compile very fast, but ultimately runs somewhat slow. It was designed for GUI applications that you're supposed to shut down and start up often. The server JIT, server VM, called C2, was created for exactly the opposite use case. We're not going to start up very often. We're willing to take a little longer to start up. So compilation speed is about 4 times what it is with C1. But it produces faster code by a factor of about 2 on average, and sometimes much, much more than that. And we want to take those two things and join them together. We want to use C1 first for quick startup, and then C2 second for peak final throughput. And that was added as an experimental feature in Java 7. It was made the default in Java 8. The actual workflow for tiered compilation is a bit more complicated than I let on there. There aren't, in fact, 2 or 3 tiers. There are actually 5 tiers. Tiers 1 through 3 are all C1, i.e. the client JIT, with different levels of instrumentation overhead. The normal flow is to do exactly what I described. Start off in tier 0, the interpreter, and go from tier 0 to tier 3, which is C1 with counters. And when those counters trip a threshold, we'll try to compile in C2, and profiling, which is detailed branch information, information about which types are flowing through dynamic call sites, all sorts of things that are important to optimizing Java. Now, when the application first starts, C2 is likely to be very busy. That's when we're doing most of our compilation. And since C2 is relatively slow, its queue might get rather backed up. And we're not going to be able to take advantage of all that extra instrumentation, all that extra profiling right away. So it might be better to just go to tier 2, which is C1 with just counters. And then if the method stays hot, then we'll go to tier 3, gather some more data, the profiling information, and then ultimately on to tier 4, which is C2. And then there's this other interesting case of a trivial method. C2 is very good at things like loops and other sorts of control flow, and that's really where it has an advantage over C1. But if you've got a simple method, then C2 is overkill. We could just use C1 and that would be sufficient. So for a simple method, we'll first try to compile it at tier 3 or maybe tier 2, and C1 will recognize that wasn't very difficult. There was nothing here that C2 is better at than C1 is. So we'll immediately recompile, not even waiting for counters to trip, in tier 1, which has no overhead, no counters, and no profiling. The really interesting thing about Hotspot's numbering scheme is, well, tier 4 is the fastest, as you'd probably expect. Tier 1 is actually faster than tier 2 is actually faster than tier 3, because of the extra overhead those things involve. But those are steps towards a goal. Exactly when all this happens is controlled by a couple different counters, one called the invocation counter and another called the back edge counter. You can think of it as a loop counter. When the invocation counter passes a certain threshold, we compile an entire method. Now, when we compile a whole method, you can't use it again until the next call after the compile is done, which is why we also have this ability to compile a loop and jump into it in situ, in the middle of executing the method, what we call on-stack replacement. You are in the interpreter, and now you want to run this loop while you already had the method on the stack. For that, we have another counter that we can compare against a back edge threshold, and that's how we compile hot loops. But we actually take the sum of those two counters and compare it to a general compile threshold as well, so that we can compile medium hot methods with medium hot loops. You know, if you have something like array list index of, and you have an array of size 100, well, your loop's not super hot, but you call index of moderately often, maybe 100, couple hundred times, you'd still like that to be compiled because you have a piece of code that you're running just as much as an isolated method without a loop. And so we actually take those two together to be able to handle that case. If you're really curious about what the exact thresholds are, then you can use, let's close the side panel here, just so we have a little more view. Then you can run Java with print flags final and just grep for threshold, and you'll find the various thresholds. Java 8's thresholds can be a little deceptive. They're specified by tier, but they're also adaptive. So this number isn't hard and fast exactly when you're going to hit. But these are the rough points at which you advance to the next tier. And then for Java 7 or non-tiered mode for Java 8, you can look at the back edge threshold and the compile threshold. And in that case, we just go straight from interpreter to C2. So to create a rough mental model of what's going on, we start off in the interpreter, we run for a little while, we hit our counter passes some threshold, we trigger a C1 compile. At some later point in time, that C1 compile will be installed, and then the next call will start using it. And then at that point, we'll be running at about maybe 5x faster than the interpreter, sometimes much more than that. Then we'll run a little while longer, more ticks of the counter, usually like tenfold more, but because C1 is so much faster, the actual wall clock time will be the same or less than the transition from interpreter to C1. But we'll then trigger a C2 compile. When the C2 compile gets installed, the next caller will then go to C2, and we'll now be running 10, maybe 100x faster. It depends a lot on the composition of the method. And individual methods really do go through this discrete phase transition. If we're looking at a whole application, then it tends to be more like a curve, because we'll have tens of methods that are important. They're all going through these stair steps, but the net effect of all of that is a curve. And this is a real curve, actually with Zing, not with Hotspot. And just to illustrate the various tiers, I did this diagram of running a spec benchmark and showing the active tiers of compilation at a given point in time. And we can see the vast majority of compilation happens very early, within the first minute or so. And in the very first minute, because we're so busy, the C2 queue is getting backed up. And almost all of our tier 2 compiles, that's the yellow band, happen at the very beginning. Because after that, C2's queue is not full, and we can go straight to tier 3. And then those tier 2 compiles, if that method stays hot, they go away, or they get turned into tier 3s, and then ultimately maybe tier 4s. Or if they didn't get very hot after that, then they just stay there, and they're there forever. The other curious thing you can see in this graph is there's this bump at the very end. That's actually a change in behavior of the application. This is a benchmark, and at the end of the benchmark, it writes out the benchmark results to CSV files and images and those sorts of things. So it's running a whole bunch of code that it wasn't running for the entire 10-minute measurement run. And so there's now a whole bunch of new stuff to compile. And that's why we see this pronounced jump at the very end, and including a little bit of a jump in tier 2s. So why did Java decide to go with just-in-time compilation instead of ahead-of-time compilation? Well, one reason is just warm up and run once code. There's a lot of code in any application that really only gets run once, like loading the classes, or setting up some caches, or loading a config file. And they're not run very often. And they're not really worth JITting. If we look at the history of, say, another JIT, like V8, which is used by Chrome, they started off only having a JIT, no interpreter. But very recently, they added an interpreter just because they didn't want to waste the time JITting code that only ran once. And Hotspot's always had an interpreter, and that's probably going to remain so, although we will talk about Java 9's AOT a bit briefly at the end. But there's just a lot of code that we're only going to run it once, and expending energy compiling it isn't necessarily the best choice. But more to the point, from my perspective, Java is a dynamic language. I know everyone thinks of it as a static language with lots of ceremony, but for me it's dynamic. At least it's dynamic in comparison to, say, C or C++. Java is dynamically loaded, and in Hotspot it is lazily loaded. It is lazily initialized as mandated by the spec. It is runtime checked, and it is by default dynamically dispatched. That's a lot of dynamicism that doesn't exist by default in C or C++. And we're going to have to be good at those sorts of things to be able to optimize Java well. And as we're going to see, a JIT has a strategic advantage in light of these things. Just thinking about what it's like for the JIT to deal with an unloaded class for a second. we compile a piece of code after it gets hot. We pass one of those thresholds I mentioned earlier. And at the point we pass that threshold, imagine that the condition you're seeing here has always been true. And so the only class we've needed to load is class 1. The else branch with class 2, well, hotspot lazily loads. So we haven't loaded that class. How is the JIT going to compile this entire piece of code, given that class 2 isn't loaded? If class 2 isn't loaded, the JIT really doesn't know much of anything about it. It doesn't know the fields that comprise class 2. It doesn't know the methods. It doesn't know the parent class. It doesn't know the interfaces that class 2 implements. It really doesn't know anything. And so the JIT's response to this is to just basically not compile the else block. It gets to class 2 and it says, well, that's not loaded. I don't know what to do. I give up. And it installs this thing called an uncommon trap, rather than actually compiling the piece of code beyond that point. The uncommon trap is a bail to the interpreter. If you reach that point, C2 will bail to the interpreter. It will let the interpreter load the class lazily, and then the interpreter will finish the execution of that method. And we have to remember that C2 is 10 to 100 times faster than the interpreter, so when this occurs, you're not experiencing a slowdown just from the loading of the class, you're also experiencing a slowdown from running in a slower tier of execution. And if what you really care about is, say, response time, you will see that. Now, the specification allows us to eagerly load classes, and generally we could do that pretty safely, but there's another problem: class initialization. The specification mandates that class initialization must be lazy. It must be done at the last possible moment, which is the first access to a static field, a static method, doing a new of the class, or the initialization of one of its child classes. Before that, the class must not be initialized. That's very different from C++, where initialization order is undefined. In Java, it must be lazy. And if you try to force initialize libraries, you'll often find that they will blow up in sometimes very subtle ways. Now, think about what this means for a compiler. If we were compiling ahead of time, every time we have my class get static, what we really have to produce in the generated machine code is something like, VM, is this class initialized? If not, initialize it. Now I can call my class get static. And that would be everywhere. It would bloat the code size by about 20%. And it would actually slow things down by 5 or 10%. So it would have a fairly large impact. But the just-in-time compiler has an advantage. It runs late relative to class initialization. Because most of the initialization happens early, while we're in the interpreter, or maybe C1, by the time it gets to tier 2, or the optimized JIT, C2, usually the classes have been initialized. And so now, at compile time, the compiler can say, is that class initialized? If so, wonderful. We don't have to put in any checks. Because once a class is initialized, it can't be uninitialized. There's no going backwards on that. So we don't have to do any of this extra overhead. We can make the code a lot smaller. We can make it run faster. And since it's so uncommon that classes are not initialized at compile time, well, we use an uncommon trap for the other case. But this does mean if you try to, say, warm up a piece of code without having classes initialized, you might be leaving traps all in that code that'll blow up at some later point in time. So you have to be very careful. Again, if you really want to see that this is happening, you can look at the log compilation. You can find the trap installation by looking for task tags with an uncommon trap inside of them. This is the compiler running, and that's logging the actual installation of the trap, as you can see on the left. And then you can look for another variation on the uncommon trap tag, which denotes actually hitting the trap, which you can see on the right. And usually when you hit a trap, the compile is made not entrant. That is, the VM decides to stop using that compile anymore, which is what you're seeing in the lower right. The other advantage of compiling later, besides just, say, class initialization already being done, is it provides an opportunity to gather information before we run the C2 compiler. And that's what's going to enable all the cool speculative optimizations that allow us to deal with other forms of dynamicism, like dynamic calls. To add just a bit to the mental model from earlier, you can basically think of, while we're in the interpreter in C1, there's this brief sampling period where we're profiling what the application does. We're following it around. We're seeing, is this branch always true? Is this branch always false? What call types are flowing through this call site? Does a null ever appear at this call site? These sorts of things. There's actually a brief period at the very beginning of the application where we don't sample at all. And this is, again, because there's a lot of one-time setup behavior in any application, and it's going to do some weird things at the beginning that it's just never going to do again. And so we don't really want to profile that. So the first few invocations of any given method are not profiled in Hotspot. After a small period of time, it starts profiling. And then this profile is ultimately fed into C2, and that's when we really reach full speed. This difference between profiling and not profiling is the difference between Tier 2 of C1 and Tier 3 of C1, as I showed earlier. But it does come with a fair amount of overhead. It's about 30% to do all of this instrumentation to gather that data, which is why we don't want to do that at the startup if C2 cannot use that information right away. So we've seen a couple examples already of what triggers deoptimization. We've seen unloaded classes and uninitialized classes, but these speculations will lead to other flavors of deoptimization. One simple one is what's called unreached in earlier versions of Java of Hotspot, now called unstable if in late versions of Java 8. But the idea is, if we have a branch of an if that's never been used, we will eliminate not the branch itself, but either the if part or the else part accordingly, if it's just not been run at all. And you can demonstrate this yourself. You can take this program here, where I have a thing variable that's initially set to null, which means when we call hot method shown on the right, we're always going to run the if part, which just prints out nothing. And I'll run that 20,000 times, which I know is enough to trigger the JIT. I wait for the JIT to finish, and then I set thing to actually be equal to something non-null, a new object. And then I run it some more. And what you're going to find is the compile that was created at the beginning of the program is going to get thrown away because the else portion of hot method was compiled to have a trap, even though it's actually printing out the empty string as well. This example is admittedly kind of silly, but at least you can see what happens. If you run with print compilation, you can actually see this occur. You'll first see a Tier 3 compile, and then a Tier 4 compile. And then you'll see the Tier 4 compile made not entrant. And I told you this often happens after a trap. That's what occurred here. And then we're going to go through Tiers 3 and then 4 again. When we hit that trap, Hotspot records, oh, we did actually go down the else path. I should compile that next time. And so the next time we get to Tier 4, that is C2, it will compile both the if part and the else part. You can look at log compilation and verify this. You can find the branch data in the compile portion and the installation of the uncommon trap, as you can see in the top right. And then you can find it actually hitting the trap, as you can see in the lower right. If we plot the uncommon traps being hit over time as an application runs, as I've done here for the spec benchmark from earlier, we'll find that the vast majority of them happen at the beginning of the application. This is separated into 5-second time buckets. But we'll also see it happen at phase changes in the application. We can see the phase change before on the far right that I talked about, where we're writing out the benchmark results and suddenly we're running new code. But now in this view, we can also see this small phase change about 15 to 30 seconds into the run. That is the point where we transition from loading the JDK and just doing class loading and starting the VM itself to actually running the application. So there are these little minor phase changes that occur in almost any application, and that's one of them. But you can see after we get past that, there's a very small number of traps for the next 10 minutes while the benchmark is running until we reach the end. So adding just a bit more to our mental model, we're going to hit some of these traps. We're going to bail to the interpreter. That thread is going to run slow, but we're going to record that anomaly, that deviation from the profile we collected in the beginning, and we're going to go back to the interpreter in C1. And when we do that, we're going to gather a little bit of extra sampling information. Now, that whole time we were running into C2 in between, none of that was being recorded. We only record the exception to the profile when we hit the trap, and then maybe some additional information while we're back in the interpreter in C1. That will drive C2 to make slightly different decisions and run ever so slightly slower. So at first it sort of over-optimizes, and then it will end up backing off a little bit. But this is the transition that any method's going to go through. So we have to ask, of course, does any of this really matter to you? Well, if you want raw final throughput, absolutely the speculative optimizations matter. They easily give us 25% over what we would get if we didn't do all of those games. And often even more than that inside of a loop. We are actually much better than C++ at handling virtual calls, i.e. dynamic calls, inside of a loop. But they do come with these costs in terms of dropping down to the slower tier and giving up some predictability. The unfortunate part is when you bail to interpreter, you almost always make non-entrant, which is basically locking out new users of that compilation. Now, the actual operation is lock-free and doesn't require stopping the world, but it does have a real downside. New callers, after one thread has hit the trap, will also bail to the interpreter. So it's not just the thread that, used the new type or went down that other branch or had a null pointer exception that's going to go slow. It's all new callers after that occurred. This isn't true for every trap, but it's true for most of the common ones. Now you might be wondering, well, what about C1? We have this tiered compilation thing. Why aren't we using it? Well, in Hotspot, the way we promote from C1 to C2 is by locking the C1. So it's been discarded by the time we get to C2, and we don't have it to fall back on when C2 hits a trap. We've actually made a slightly different decision around this in Zing because we want to have at least a somewhat quicker fallback. Here I'm showing the same benchmark from before, showing traps over time in 5-second time buckets, but also showing tier 4 compiles that were made non-entrant. And you can see these are very strongly correlated. There are some traps that won't make non-entrant right away. You might get 2 or 3 strikes for, say, a null pointer exception. And also you might actually have more traps than made not entrants because you might have multiple threads all hitting the trap simultaneously. But overall, they're very strongly correlated, and you can see they mostly happen at phase change boundaries. So the very beginning, the point where we start running main, and the point where the benchmark writes out results. And these traps, followed by made not entrant, lead to some really hard to identify disruptions in performance. These are not something that you can see by, say, looking at a GC log. GC logs include stop the world pauses, and not even all the stop world pauses by default in hotspot. But this isn't a stop the world pause. All this is turning off a single compile and running slower for some amount of time. If this affects a hot method in your system, this could easily be tens of milliseconds of disruption. But it's not a stop. It's just running slow. If what you care about is response time and predictability, this will still be visible, but it's hard to find. You can really only measure it directly by external simulation of the system. But there's something even worse. There are actually de-optimization pauses. Hotspot performs an optimization called class hierarchy analysis. There are actually a couple flavors of this. I won't go into the two different flavors, but the basic idea is, let's say I have an abstract class, func, with an apply method. And because classes are lazy loaded in Hotspot, maybe I'm only using one class right now. There may be lots of other functions in existence, but right now I'm just using the square function. That's the only one that's been loaded. So at compile time, C2 will see that, and it will say, well, there are only two possible outcomes to calling func apply. Either the object I have is a square, and I'm calling square apply, or the reference is null, and I'm throwing a null pointer exception. And it will optimize accordingly. So you can write a simple program like the one I have on the left here, where a function is initially a square, and I have a whole bunch of apply methods which are just wrappers around func apply. You can imagine they're scattered all over the program. Of course, I just embedded them in one place. And again, we let all of those get hot. We wait 5 seconds for the JIT to kick in. And then all we have to do is load one other function class, square root. And chaos will ensue. The reason chaos ensues is the way Hotspot does class hierarchy analysis is when it produces the code, it produces an unguarded devirtualization. For the other cases we've seen so far, like the unreached or unstable if, we have to keep the condition, and that acts as a guard. So the code will check if it's incorrect, and it will uncommon trap and go back to the interpreter. In this case, there's no check. It actually will just call square apply directly with no type check to verify that the function really is a square. And then it will probably actually go a step further and inline that as well. But that means as soon as another class is loaded in this class hierarchy, the code is wrong. And the code can't detect that it's wrong. So all of this code has to be killed immediately at a stop the world pause across all the callers. And you can see that happen. If you run that program, you'll see that you will get a lot of tier 4 compilations of these various apply methods. They will all have inlined square apply. You could see that by turning on print inlining or looking in log compilation XML. And then as soon as I load square root, and all I have to do is load it, not even use it, you'll see a ton of non-entrants for all of those apply methods. And then if you're running with a couple more flags, print safe point statistics and print safe point statistics count equals 1, you'll see other stop the world pauses besides GCs that happen in Hotspot. And one of those is DEOPTIMIZATION. And that's what you're seeing at the bottom. You can also, of course, see this in the log compilation XML. You'll see these dependency failed tags that will tell you the reason the dependency failed, the context, in this case, the hierarchy of is function, the specimen that we were originally basing our assumption on, square, and the class that caused us to violate the assumption, square root. And then you'll also see non-entrance. Strangely enough, I don't think you actually see the DEOPT pauses in the log compilation XML. You do see everything else. Again, we can plot these for the spec benchmark from earlier. And we'll see that these failed dependencies are much fewer in number than traps, and usually most of the not entrants are triggered by traps. So it's much smaller than the number of not entrants. They still do correlate strongly to the phase transitions, but they're actually a lot less common than uncommon traps. Now, you might have been scared by the fact that this is a stop the world pause, and perhaps rightly so. There's actually something more terrifying about these. I told you for traps, we lock out the old compile, and all new callers bail. Well, for DEOPT safe points, all returning frames also have to bail. So now it's not just the thread that loaded the class, it's not just new callers into the compilation, it's any thread that has this compilation on its stack anywhere will eventually bail to the interpreter. That can hurt tremendously if it hits a hot method. The pause itself is usually single millisecond, but can certainly be up to tens of milliseconds. But the real problem is those downstream effects, which can be, for a hot method, hundreds of milliseconds of slowdown. Fortunately, Hotspot does have another way of doing devirtualization that is guarded and doesn't have these ill effects, but Hotspot doesn't give you an easy way to turn off CHA by default. It has ways to do it, but they're only available in development builds, as far as I know. Again, you can see this by looking at log compilation XML. What it does is it keeps a profile of the call, what types flow through the call site, and will predict those calls, and it will still devirtualize and inline those calls. And then down the else path, we'll actually install an uncommon trap rather than a virtual call, because that lets us keep cool loop optimizations that you'd have to give up in, say, C or C++. But does have potential downsides in terms of latency. Okay, so we've seen a couple flavors of de-optimization. We've seen uncommon traps, and we've seen DEOPT pauses. Let's talk a little bit about possible mitigations. Before we can do that, we really need to talk about what is your goal. If your goal is, say, startup time, perfectly reasonable goal, then you might want to make different choices than if your goal is peak performance. If your goal is peak performance, you want to keep all these cool speculations as much as you can. But that might run afoul of some other goal like predictability, and predictability might create a problem for something else like first case response time, depending on where you need that to be. So you don't have a great deal of options in terms of mitigations with Hotspot. One of the things you could do is you can preload your classes. This helps a little bit. It will help us from installing uncommon traps for unloaded classes, logically enough. It will help with avoiding the worst cases of DEOPT pauses, because as we saw, the problem happens when we load that extra function class. If we load that extra function class up front, we can avoid that DEOPT pause later, but that will come at a bit of throughput. Not much, because there is that other devirtualization strategy, but it will be there. And so you're going to have to make a choice. If you're a little more brave, you could try to pre-initialize your classes. And if you weren't aware, if you just call class for name the way I'm showing here, that is actually pre-initializing your classes. But this can get into a lot of problems very quickly because of sensitivity to class initialization order. If you control all the code and you can fix any initialization order problems, this can work. If you're using a lot of third-party libraries, this probably isn't going to work for you. What a lot of people end up doing is just giving fake load to the system. This can work, but you have to understand the system optimizes for the data it sees at the very beginning. And so if the very first thing it sees is fake data, what it optimizes for is fake data. And if your fake data isn't representative of real data, you're still very likely to trap once you start running real load. There are places that do this. Facebook sends face traffic to their system to warm up after a new code deploy for their hip hop VM. But it's not perfect. And it really becomes problematic for anything that's transactional. You know, if your system is read heavy, like Facebook, this works fine. But if you don't want to actually do a mutating operation, now you've got some challenges. I mean, you could try to do something like I'm showing with the pseudocode here, where you say, if my system is warming up, abort my transaction, else commit. But then what has the system optimized for? It's optimized for aborting transactions, which is, of course, not what you're going to be doing most of the time after you start running real load. And so you're just going to trap immediately, throw away those compiles, and it's debatable how much this warm-up really helped you. So you have to be very careful. If you're going to go this route, you really want to look at not only your response time, but look at, am I doing a lot of compilations that are just being dropped on the floor? And now you know how to do that by looking at the log compilation XML. So I promised to say a little bit about what this means for an AOT, and I'm going to do that now. As you've probably seen or figured out by now, the challenge for an AOT is it wouldn't get the benefit of a profile because you can't have that until you actually run the application for a little while. And also, an AOT would have to run before class initialization, and it would have to put in all those extra checks. Or we just live with that overhead and we give up on all the cool speculations and let our Java code run slower. Those are really our choices. We could choose nice, stable performance as one option, but slower than final throughput could be. Or we could choose peak performance. We could start off in a nice, stable mode, then profile, over-speculate, drop down to a slower state again, and then get back to a higher final throughput position. That's possible. And actually, the Java 9 AOT has both of those modes. It has a non-tiered mode, which uses conservative compiles, beautifully stable, but not going to give you the peak throughput. And it has a tiered mode that does this usual workflow with the added benefit that you don't fall back to the interpreter, you fall back to that baseline that you started with. What we've done at Azul is we created a thing called Ready Now that actually takes all the information from the original run and puts it in a log file. And then we can use that information in subsequent runs so that we can keep all the cool speculations, but also get predictability since we've already seen all the things that cause deoptimization and can avoid a lot of them. Essentially what this is a profile cache. It is not a JIT cache. It does not store compiled code. It stores all the data that influence the compile so that we can roughly replay the compile next time. And this works quite well. If you look at the blue line here, this is the same benchmark running on Zing that I've been showing for Hotspot. And you can see it took a while for it to warm up. But I took that information, I put it into a log, and I fed it back into Zing the next time. And on the second run, I got the green line. We're starting off a lot faster. There's still admittedly some volatility, but I did that one more time. I produced one more file, and that got me the orange line. Now we're starting way faster than we were before, and the orange line is quite flat. There's very little volatility. And in this particular case, this benchmark actually runs faster in this mode. I wish I could say that was true of all benchmarks, but that is the case here. Just to leave some time for questions, I'm not going to go through the last couple slides on the details of how ReadyNow works. I'm just going to say, I do want to indicate that I'm not saying that our solution is better than Java 9's AOT. It very much depends on your goal. If your goal is startup time, the Java 9 AOT might be better. If your goal is predictability and you're willing to give up peak performance, the Java 9 AOT might be better. If your goal is peak performance, predictability, and you want pretty good first response time, then I think our solution is better. There's no one right or wrong answer to any of these problems. Okay, so hopefully you have a better understanding of all the parts of the hotspot lifecycle. We've at least seen a little bit of what goes on. I mean, I could go on for hours, but you've seen a little bit of the profile data we gather, a little bit of the what causes deoptimization, and hopefully you have a little bit of a better feel how this all feeds into warm-up problems. If you'd like more information, I'd recommend you go look at blogs by various people who work on the VM. Chief among them, Alexei Shipalev, who was at Oracle until very recently. He is now at Red Hat working on the Shenandoah collector and has done all sorts of interesting performance measurement and talking about the things that go on inside of Hotspot. So if you want to know more, he's an excellent source. And if you'd like to know more about ReadyNow, you can follow the link to our website at the bottom of the screen. So thank you all very much for listening. If you have questions, please, I will answer them now.